So, welcome. I suppose this is lecture number 12, isn't it? We've gotten really far. We've written down lots of equations of motion. There's one left. Let's see what we have thus far. The scalar field. Is that a headline? Something like it. So this is the equations of those. Okay. The scalar field. Box written this way. If it's a massive field, it's an m squared phi equals 0. It's if you solve this equation, it's one set of, well, for every momentum you have an arbitrary coefficient. It's basically the amplitude of your partial wave. I count this as 1 degree of freedom. It describes one particle. If you make this complex, which we'll do later today more explicitly, then you just get a second copy of it. You can think of the two parts. We have 2 degrees of freedom. We can think of them as particle and antiparticle. The complex conjugate is sort of the one with the opposite charge. And we won't see this today, but maybe tomorrow or next week, how this complex conjugation is related to the antiparticles. We haven't really done any particles at all. It's just the classical field. Then we had the Weil spinners. So there's the left-handed by L. It could be 0. Then so I'm going to add the mass term. Let's get it now. M sigma 2 sine 0. This has 2 degrees of freedom. If this is 0, then it's a particle moving at the speed of light with a definite helicity. It's always left chiral. That's this L here and the L there. It's always the same representation on the Lorentz transformations. But the equation of motion, if this is 0, no mass, says this particle has left helicity, which means the projection of the spin onto the momentum is -1/2. So it's basically opposite. And it has an antiparticle friend. This has the opposite helicity. So it's a particle of left helicity and an antiparticle of right helicity. Also, this is a preview of what we'll do and see explicitly. If you add the mass term, it's the equation doesn't say anymore that it is left handed, left helicity, because it's not equal to 0. So then you mix the two, and since there's a star, you also join particle antiparticle. So again, you have still 2 degrees of freedom, but they are not particle left-handed, antiparticle right-handed, but it's the same particle and antiparticle, but now both helicities. Then we have the Dirac spinor field equation. It's now 4 by 4, so the different matrices here, connecting the spinor index of our field in the spacetime, minus m psi equals 0. This has 4 degrees of freedom. So now we have everything. You have particle, antiparticle, and each of them have both helicities. They want to, and then you superposition. Then we also moved to the vector field, and the naive equation was d mu a mu plus n squared a equals 0. And then we realized just by writing the letter a mu, you're not guaranteed to have a vector field, right? You can call everything. You know, just because I call something x, it doesn't have to be position. Just because I call it t, it doesn't have to be temperature. It depends on where it appears. You can call everything U1. This is the canonical letter for a vector field. Really, it is the canonical letter for a gauge field, but we don't know what this is yet. So this is a vector, but just because I write it doesn't mean that the equation behaves the way I want it. So that's just for scalar fields. It's this equation where I have just added an index here. So we have to do something more to get a generic vector field, one where you really make use of this index. So you couple it to let's do this a mu with the derivative, and now this index has to transform in some non-trivial representation, the defining representation of the Lagrange group, because this does. And if the two together should be invariant, then this has to transform in different representation. Here, without this term, this could transform as it wants, even in the trivial representation. And now it doesn't fit in this equation, so we have to add another derivative just to make the whole thing transform the same way as here. There's an uncontracted index, so we want it there. And then we worked a little to figure out what the sign should be. And we found out it's 0. No, sorry, the sign is minus in order. If I hit this, I want an equation for the divergence. So this equation hit with d mu, then these two terms go away. Let's see, then we have the derivative goes through those, so we have divergence of A. And here we make another box. So we have box of divergence of A, box divergence of A. So these two cancel, and we are left with the divergence of A here with an M. And so this sets the divergence to 0. So what this really is saying is the equation that we didn't want, d mu A mu minus plus M squared A mu equals 0. But in addition, this thing. So then we have like 4 solutions here, but we have this constraint, and that sets essentially one of them to 0. To make this concrete, we introduced the polarization vectors, and the solution to this equation now was a superposition of 3 polarizations. Let's say, so we defined mu epsilon mu, which has to depend on p, and then there are three solutions. I equals 1, 2, 3. This equation has 3 solutions. This is basically this condition. This has to be 0, and then we can write this somewhere. Our A mu of x is integral d p pi 1 over square root. This is really just conventional. We have no idea why this is so. The reason why this is so is that later these, after quantization, will turn into oscillators, and they are properly normalized as ladder operators if we have all this junk in front. So then this is a function of p. We can choose for every p the coefficient, and this I is really the physical polarization. So multiplying this by this I, and then here the mu index to sort this up, and then p and e to the I to the x. And that's called the positive frequency. There must be a minus sign, because it wouldn't be positive. So minus, sorry, just taking my minus signs. This also differs from reference to reference, because there's the metric in there, and my metric is plus minus today. And then plus the other part, the negative frequency. And since this is supposed to be real, you have to conjugate this epsilon I. Somebody chooses complex polarization vectors. You can if you want. For example, circular polarized light or whatever it is, it's massive, but you like to have an I in between the phase shift, and then each of these have a few X done. Okay, so this was the solution for this. And what was left to do, what we'll do now, is to discuss the massless case. So this is the massive field, and the equation is really called Roca equation. And now we also here always discuss the case m equals to 0, and it was very simple, just set it to 0. Here was the only interesting thing happening, but only in terms of the interpretation. Formulas were very simple, and it just went through what I'm saying. The degrees of freedom are the same, massive or massless. If it's massless, it goes faster. And if it's massive, you can actually slow it down and put it at rest in your frame, or you can follow it. But nothing more happened. And here, something will happen. If, so massless, now, let's get a name, just massless. It's still the 4, but then further down, massless vector field. We can, of course, set in the Roca equation m to 0. Then we have d mu a mu minus d mu a mu equals 0. And that's called Maxwell equation. Earlier, just when I introduced all this business with field theory, we had Maxwell's equations in terms of the electric and magnetic field, and they look totally different. But it's still the same when you realize the following. Let's pull one of these derivatives out, d mu, and then we have mu a mu minus d mu a mu. So that's these two. And you can swap these if you want, but that's this combination. And that guy actually has a name that's called F mu field strength. Field strength. And so the equation in terms of the field strength is very simple. It's this. It looks even nicer than all this index mess. And the field strength is now these two components. It's a 4x4 matrix if you write it down, because there's two formulas, and it's anti-symmetric, which I can see here. If I change mu and nu, then the first and second term change place, and there's a minus in between, so it's anti-symmetric, which means there's nothing on the diagonal. Just put index 1, 1, 1, 1, cancel, 0. And then here is something non-zero, and in the standard notation, this is called E. And this is minus E. And this is B. And this is minus B because it is antisymmetric. And now just to make it a little bit more funny, the minus sign goes, I believe, there. Anyway, so it has the electric and the magnetic fields in it. That's why it's called field strength. And if you write this equation for those components, then you find some of the Maxwell equations. Which one do you find?
Homogeneous, I'm assuming.
Why?
Because there is no current. So.
Ah, that's clever, but it's the opposite. Why? Because they're not here. Well, in a sense, they are the homogeneous ones because of their currents, but they're not called. And what you find is the inhomogeneous Maxwell equations with the currents and charges set to zero. That doesn't make them homogeneous. It's in that terminology. The reason is here we would have a current. So here you have to replace J mu, and then you would find the ones with the charges. We don't have it here because we are talking about three things. It'll be in the homework, in fact, where you find something there. So this equation are the inhomogeneous Maxwell's equations, so two of them. That unit, but the currents and charges set to zero, and the other follow how do I say that? They
Were the other equations related to the dual tensor? Because I just
yes,
remembered my electron.
it's right, exactly. You can do epsilon mu rho sigma the mu say oh, that doesn't work. The mu rho sigma. This is the homogeneous ones. And the reason why this is true is the fact that the F was written like this. So here, this could be any old F that is antisymmetric, but it doesn't have to be the derivative or the antisymmetric derivative of some A. So if I just have an antisymmetric F, then this combination isn't zero. Right? It's whatever it is. It's the derivative of this antisymmetric thing, and here it's just antisymmetrized with this extra index, and this is just hanging. But since the F is d rho a sigma minus d sigma a rho, since it's this thing, that is actually zero. Why? Because now you have the nu and the rho, two derivatives, and the two derivatives commute, but they are connected to an antisymmetric epsilon, and therefore this is zero. So these homogeneous equations just tell us that your F in this equation originally was expressed in terms of this A. That's all very interesting, but it's not the point right now is not very relevant, but I'm saying all this to connect it. So, like, why is this Maxwell's equation? Where I know E and P and divergence and stuff. And so, written in terms of these components, but if you want to write it in these components, you first have to go through this F, and we are here, and then you find what we just said. So that was only to justify the name. And now we want to see what's the solution. Does it look like this? In here, by the way, everywhere in that where the P is, here's just the vector. Here is the zeroth component, so the P0, it's P vector, and that is P squared plus N squared. This is understood everywhere. Didn't write it, should have. You should write it in the so the time part, the zeroth part of the momentum is fixed. It's also always nicely positive. So do I get now as solutions to this equation, or this equation, the same expression, just setting the m to zero? And the answer is not really. Because it'll turn out, I'll try to argue now, that you lose one polarization, which makes sense from what you know. The photon has two polarizations, either up, down, left, right if you talk linear polarization, or left and right if you change your basis and you have like the complex things in there, then you have circular polarized. So now I don't know what the logic is. do we have this equation and derive two polarizations? Or is it, hey, I have a photon in mind, I know it has two, so I have to do something here. And really, the honest logic is the second. I know I want photons, and they have two polarizations. You know, I can write this, set m to 0, and it's a beautiful equation, right? It doesn't bite. And it has these three things solving that there. And I guess that works. It's just not what we want to describe a photon. So there will be something. Now, story goes. First observation is the divergence of A is no longer a consequence of this equation. Where is it? Here. This was the consequence, because if I hit this equation with a master, with a derivative, all of this goes away, and it still does, but then we're left with m squared good. If the m is not there, it's identically 0. Didn't I say this somewhere? It's this, really. So d mu a mu is no longer the consequence of the equation of motion, and no longer means or equals 0. It was for n not equal 0. And second observation is if a mu of x solves, can you give it a name, Maxwell? Well, instead of writing equation number 50,000, this is the equation I'm talking about. So if FA solves Maxwell, then A mu, which I call prime, which differs from this one by a function alpha of x with an additional derivative. Then it solves Maxwell. Two. So you pick anything you want, any complicated function of space and time. You can't pick 4 so that you change every of the 4 components individually. You have to pick one function, take the derivative so that you have like 4 gradients of this one function, and then you add this to the 4 components here. It's a little less than choosing arbitrary functions to everyone, for everyone, but it's a lot of freedom because it's a function. It's not just adding a constant or so. It could be very complicated. And that's just what it is. And you could, in principle, leave it at that. Have a huge symmetry, which means you find one solution, and you can also find easily another. Just add your favorite function to it. And that's good. But now we do something else. We say the new solution that you get out of this first solution, like the old, by adding, we do not want to consider as really a new solution, not something new. We want to identify the two. We want to say that this A and that A prime are equivalent. They are to be identified. Does that make any sense? Let's think of something.
Like they describe the same physics.
Yes. Yes, and it's not so. I This is very spontaneous. It might not be the very best idea, but let's say we have a particle so that moves in this blackboard here, and we look from the top. So this is our, so look from the top, this is the arrow. Then we can see that it moves left and right, but we don't really see towards us and away from us. Say there's no perspective. We only have one eye, and so we don't see the difference between is it here or there. So this is just my setup. This is why it's a spontaneous, stupid idea. But this and this is the same. And now you have a particle motion in this plane. So we have an differential equation that solves for this forces, and then we have this trajectory. And so this is an r vector, so it's an x and y of t. This is my solution that represents this thing here. But since I only see, like physically, it has gone here and back, like an oscillation. I could, in principle, have chosen very simply straight line, turning around and back. This is a very different function, but it looks the same. Basically, this component is irrelevant. And so I want to identify them for some reasons, which here aren't clear at all. In fact, it's totally contrived. For some reasons, I want to describe my system, the equation of motion, with these two components. They look nicer or so. That's what's happening there. But they are not to be distinguished. Like this is the same as that. So you want to identify the two things. So if I have an R, vector, that's my A of t, an R of t, then an R prime of t, where I add nothing to my x, but whatever you want to your y is the same thing. Because it does in x here, it does the same, and in addition, it goes wild here, which I don't see, I projected out. So I have essentially I have too many degrees of freedom here, but then I identify lots of things. In fact, everything, yeah. Is that, yes.
Why do we need the derivative?
Here I don't. Here, let's see why. Proof. That's funny. Proof. Sounds like we know what we're doing. What I need to show that this works, right? Or even better, what is f? F prime mu is d mu a mu minus d mu a mu. So that's the definition of the field strength for the primed one. And that inserted is d mu a mu plus d mu alpha minus d mu a prime plus d mu alpha. Not just no prime. I inserted the primed one. Then the first two in each term together will be the f mu without the prime, and the second cancel because I have the derivative. If I didn't have just the a, first of all, I wouldn't know how to write something like this. I could do this. I could do alpha. Let's do this alpha mu. Everybody gets their own. Then we would have here plus d mu alpha mu minus d mu alpha mu, right? So that would be the additional thing. And that's something. It's not no contradiction yet because that's not the equation of motion. I should still hit it with a derivative and see what happens then. So if I just hit this with a d mu, then I get something that doesn't vanish. But if I have the derivative here, then this is d mu alpha minus d mu alpha, and that's zero. So Posic is f mu nu, and since the f is already the same for the A and the transformed one, the transformed will just have the same equation of motion, because now you get to go d, we have to do this, now d mu f prime mu mu, but that is d because they are the same, f mu mu, and that's zero because we claimed it solved it, so the other one's also two. That's why you need it. In my toy example down here, it's not necessary because it's a different thing. It's just a picture. I wanted to show you that there could be situations where, for some reasons, you want to write equations that have more degrees of freedom than the configurations that you want to describe. In this system, this is really a one-dimensional thing. And the particles go only along this axis. But for some reasons, I prefer to have a two-dimensional, and then I say everything that differs by the vertical motion, I identify. I'm not sure if you've encountered this thing. It looks unnecessarily complicated, but this is what's going on here. Also not necessary. We could say we live in this, like, we have this extra degree of freedom, then we would have this equation, just the M0, and we have three polarizations. But since we know our goal is photons, they have two, so we want to get rid of one. And here we are invited to do this. We identify them, and then in a minute or 5, we will show that this identification gets rid of an extra polarization. Where was I? What was it now? I do the 5 minutes. Yes. Did they just come up with this, or what? Why do they say this is an identification? Because here, going back to the equations in terms of E and B, that's really how you start. You go like divergence. Well, that one is the homogeneous. I want the homogeneous one. So curl H minus d dt and E is 0. So and then they liked hey, we can solve this equation by saying that B is curl A, and then this is satisfied because the divergence of a curl is 0 always, and then I don't have to worry about this. I can insert this here in all the other places, and then I work with this A. Plugging this in here, you see that the curl of E plus A is 0, and then you call this the gradient of another field, and then you have your E is minus the gradient of a phi. Let's say phi because it's not our scalar field, minus A dot. And now you express your E and B in terms of A and phi, which really is our, not sure if it's up or downstairs, minus there, oh, there's a minus there. Forgive me, it doesn't matter, it's just a sign. So you chose to introduce the potentials to solve two equations, and then you have the inhomogeneous ones, and then you realize I could have used different ones. If I add the gradient, if you just add a constant to it or so, then it disappears because the phi only appears with the derivative. And so from there, they were already primed, right? They knew, oh, there is this freedom in choosing my potentials. And then you call it the gauge freedom. So this really here is then the gauge freedom. And in our discussion, we came from a different angle. We just said we had an A mu, that's a vector field, that's right on the equation of motion. And then we ended up with something that looked like Maxwell's equation, and then we realized, oh, wait a minute, okay, we have to take the symmetry and understand it as not something that relates a solution to another, but that identifies two solutions and really think of them the same. Yes. So this was already kind of clear from here. Now, what's the consequence? The consequence is one, that we can create this condition, which wasn't a consequence of our equation of motion, but which is an option now. Why is it an option? Because let's say we have an A that doesn't satisfy this extra condition. So in case d mu, a mu is not equal 0, and we call this f, I guess. That's non-zero. Then, first of all, solve. Then solve box or du alpha equals, I think, minus f. Let's see if it comes out. Whatever you find, computing the divergence, use this in your equation and solve this. Now you have to show that the solutions exist. Let's say they exist. Then we use this alpha as our object here, which is called the gauge parameter, or I guess gauge parameter. It's a whole function. So the equation is called the gauge freedom or gauge transformation. It's the gauge transformation, which is allowed because of your gauge freedom using, it's written in terms of the gauge parameter. Everything's gauge now. And then we have an A, and then set A prime, A mu plus this alpha, D this alpha, and then the condition is there. A mu prime is D mu A mu plus D mu D mu alpha, just by plugging it in. This was F, and this we have designed to be minus F, so it's 0. So whenever you have a gauge field, now I've started to call it a gauge field, the vector field, whose that for divergence isn't 0, you can move to an equivalent one whose for divergence is 0. The picture is this. If this is the space of all gauge fields, of all vector fields, I don't want to call this gauge fields yet. So this is the space of all aliens. Every point is a whole function. It's a set of 4 functions. And so this transformation relates many of them. And for example, this one is related to everything on this line. Does that make, do you understand what I'm doing? Yeah, one at least. I have a function just represented by a point. I should have drawn a whole function, but then I don't have room in the blackboard. So that's this function, and then I move with a choose an alpha, and it goes here. There are other things. This one, for example, they are really different. In my picture here, this would just be the vertical lines. You can move up and so yeah, not good. So and then I have things that are related here and stuff. These lines are called, by the way, gauge orbit. This is a gauge orbit. If you start with a certain field, vector field, and you do all the possible alphas, all the transformation you can, and what you can reach is your orbit, like around the Earth. And now they're in this field, there are in this space of vector fields, there are vector fields which satisfy this condition. And there are others who don't satisfy this condition or not. Where are they? They are, pick a color, yellow, they are here. These dots are also gauge fields. Vector fields are vector fields. See, should I tell you now why I get confused? This field will be used later to create symmetries for other fields. Like when we have our scalars or spinors, and we want them to have a certain symmetry, then we have to introduce this friend A to actually realize that symmetry. That symmetry then will be called the gauge symmetry for them, for the whole system. And this helper A gets the name gauge field because it helps to make that symmetry a certain way. And that's why I get confused all the time. But here it's just the vector. And so we have on this line the vector field whose point vertex is 0. And this statement here, what I do is just saying you can always go from anywhere, any vector field, by an appropriate gauge transformation along the gauge orbit to end up there. It's really a complicated and long way of saying you can always find a transformation that satisfies this thing. So this is no longer a consequence, but it's a choice that we can make. And then we call, so d mu, a mu equals 0 is possible gauge condition. So we choose it. It's not forced, we can choose it. And this gauge condition has the name Lorentz. And this is not the guy with the TZ of the Lorentz transformation, it's the other one. What was his name? Lorentz. Yeah, Lorentz, fine, but like one is Hendrik Anton Lorentz, and this is it's a different one. Lorentz condition, or Lorentz gauge, or Lorentz gauge condition, whatever you want. How many letters you want to spend? The Lorentz gauge, or Lorentz gauge condition, or Lorentz condition. Okay, now we're in business. Now we can derive the same from before. So at least we haven't gained anything. Before we had the 3. Now this went missing. We would have gone back to 4, really, 4 degrees of freedom. However, now we know we can choose it because we're identifying different things. We don't need to write all 4. Don't write all 4 because the fourth one essentially, like one of them, you can always remove right in the other form, right? So if you picked 4 different polarizations, I can always find a gauge equivalent A, which has only 3. That's what it is. And now we still have to get rid of one more. formalistic one, wait, there. It's complicated, let's do it complicated. So we have E where the condition was E mu epsilon I mu of P is 0, but now, as opposed to a massive case, the P squared is 0. And then the solutions, we had this picture last time. If this is my P, and that's a massive, so this is the 0, and this is the P vector, and that would be a massive P, because it is time-like. So this is P squared positive. Then the corresponding perpendicular, like the ones that are in the 4-dimensional sense perpendicular to this, are, well, first spatial perpendicular, but then also reflected across the diagonal. So this would be an epsilon, whatever it is, 3, let's call it 3. Mu, which is perpendicular. But now our mass goes to 0, so the P becomes a light-like one, so it moves here. And then the orthogonal one moves here too. So essentially the epsilon 3 is proportional to P, which makes sense because you want this to be 0. So if epsilon, one of them, is proportional to the P because of it, it's 0. So one polarization is in the direction of P. This means here the A is proportional, I mean, for polarization epsilon, I don't know where my index goes, here it's found. So proportional to P mu, the vector field, I didn't say any field, the vector field is A mu of, like in momentum space, it is proportional to P mu, which means in coordinate space, it's proportional to a derivative. I need a name. Alpha is, yeah, probably F is G, I don't know. Or is it alpha? Let's leave it like this and then use an alpha to remove it. Now, for this funny polarization along the momentum, the corresponding vector field is a gradient of some function. So what? But it is. But now I will use an argument like this, which also removes this bit. And so now that A mu prime equals A mu minus, so I guess I don't need to write proportional because whatever there is, I just put into the G. Because I want to write an equation with something canceled. So if there was a factor 3, well, then it's the G. Everything is in there. So the A is really that. And now set this with alpha, right, equals minus G. Well, then it's obvious, right? So cancel. Then A mu prime equals 0. So I can gauge away whatever this funny polarization produces. Just have to make sure that I don't spoil what I carefully made here, right? So we move to this line, and now we're doing another gauge transformation. And I really hope we're not going to move out of this, because if you moved out of it, then everything is broken, because it's based on the Lorentz condition. But in fact, we don't spoil it, because if our A is of this form, and since this A was in Lorentz gauge, we know that d mu A mu equals d mu is 0. We know this. We know that the G satisfies the wave equation. So and if alpha is minus G, we know that d mu alpha is 0. And then we can compute what's the divergence of this new thing, the new thing that doesn't have this gradient part. And that is d mu alpha mu here plus d mu alpha. But this thing was 0 because this is how we started, and this is 0 because we just figured it out. And so we don't spoil Lorentz gauge. So this here, this d A prime mu equals A mu plus d mu alpha with box alpha equals 0. That's more special than what we had before. Before we just had this and called this a gauge transformation. And we used this gauge transformation to demand Lorentz gauge. Now, after having done that, and after sitting on the yellow line, we can still do this without moving away from the yellow line. This is obviously this condition, and that's called residual gauge, whatever. Freedom, if you can do it, transformation, there you do it. Residual gauge transformation. And now we have both. We have gotten rid of the fourth polarization because of Lorentz gauge, and we have gotten rid of the one that is the time-like, called longitudinal. By this residual gauge transformation. And now we've gotten rid of 2. You don't need the other ones, you only need 2. Yeah. Yes.
First of all, like how can I be sure that like this is a new thing? Because it kind of looks like it's just a special thing of the gauge.
Yes, that's true.
But
That's
like,
true. When you solve this equation,
yeah,
then that solution isn't unique. This is a differential equation, linear, second order, well, it's partial, but whatever, and it's inhomogeneous. And you know, it has a ton of solutions if you don't impose further initial and boundary conditions. You have a particular solution which guarantees this F, and then you have the integration constant in there, for the homogeneous. And that's basically that freedom there. You know, this is in fact the homogeneous equation corresponding to this. So you can arrive on this line, but this little spot there is actually a big space where you can get anywhere in this big spot by picking different solutions. And then there is a good one, basically, which brings you Or we want to know. Okay, good.
The other thing is, everything that we're doing here, like it sort of require, or like it only makes sense if the A mu itself, like once we later, I don't know, add in some interaction or something, once this interaction also doesn't depend on the like choice of gauge, right?
Yes.
Yeah.
Absolutely. So yeah, this is very complicated, and you might call it interesting or annoying. It's just it's what it is in the end. But one question you can ask is, why do we stick to A mu and keep so that we have to keep track of all this gauged freedom? Why couldn't we just write an A I with I equals 1 and 2? These are the two physical degrees of freedom, and we reduce it to it, and then that's it. Because then the equations that we write don't look Lorentz invariant anymore. You need the mu index to have this Lorentz invariant. And if you don't see this at all stages, it might get lost on the way, and we don't want that. We want theories that are Lorentz invariant. It should be respect the principle of relativity. And like on the way, we're not just transforming equations. There will be a step that's called quantization, and that's not an equivalence transformation. I mean, what equivalent term form? This is not applying rules of mathematics, and then you're sure you get. There's a quantization is an inspiration. It's just being creative and write equations for a system that you don't have any idea how to come up with otherwise, except for like looking at a classical thing and then replace it. And so this replacement, if you do this in terms of this, you'll mess it up. And not you. It's messed up. And then you have to make sure that what you get is Lorentz invariant in the end. And then there could be all sorts of things. They call it anomalies if something goes wrong there. So you want to keep the A mu visible, and yeah. But then on the flip side, actually there are both ways to quantize it, right? You can first restrict to the physical degrees of freedom, then quantize, then check that you're still Lorentz invariant. That's one way. Or the covariant quantization is you stick with the A mu, then you quantize, and you have to see what to do with this gauge symmetry. You have to still do this identification of this.
But I mean more like if you want to like throw away this gauge symmetry, all of this thing that we're doing here, like it's sort of predicated on the idea that like if there's like I don't know, like in Maxwell's equations, there of course it makes sense the way the fields interact with the with matter, like doesn't depend on any choice of
Yes.
gauge. Yeah. And you kind of, I don't know, you sort of need to assume something similar for
Perfect.
Okay.
And very soon we'll like today go to the Lagrangian formulation of this, and then it will be easier. I'll introduce this in a moment, and it will be easier to write down theories. Instead of messing with the equation of motion and try to add another term there, so we add this in the Lagrangian. And if we want to do something with this vector field, massless, with this gauge symmetry, we have to make sure that all the terms that we add respect the gauge symmetry. So we'll look at the terms, and just like we add only things that make sense in terms of Lorentz representations, everything has to transform in the same way under Lorentz. Here, everything has to transform properly under the gauge transformations. And that will restrict your choice of theories significantly. And in fact, now we can, you say this in English, to let the cat out of the cat out of the box. It's alive, yay! this is how the standard model of particle physics, what is it based on? It's all gauge theory, like the photon, the gluons, the weak interaction vector, those is all, and then this symmetry we'll soon see is related to a group U1, and then you have the SU2, which is the weak, and then you have SU3, which is the gluons and all this. So this is really seems to be the world. And if you have these symmetries, it'll tape your quantum theory, like quantization, fluctuation, all this stuff can introduce things. But if you have symmetries, then some things can't happen. And so this is coming to rescue. By the way, now that you're asking, these 2 degrees of freedom are like the particles that we see and can prepare. But when we do quantum computations, like what we don't see inside that Schrödinger box, there will be the other polarizations, like around the unphysical ones. So they'll come back. But I shouldn't have said that, no. You happy now? Yeah, okay, so fine. Now you've seen vector fields, gauge symmetries. This concludes the chapter, finally, number 4, which went on forever, about the field equations. And now I'll move on, I announced it, to the Lagrangian formulation. And the question is why? First of all, you know Lagrangians from classical point particle mechanics, I hope. You remember? 4 or 5. So this is just a convenient, for one thing, it's a convenient way of writing equations that govern a certain system. So it's constraints and with feeling, but well, it's convenient. I'll make clear what I mean by convenient and give examples. What we can conveniently do, it's related to the symmetries, but for the ultimate goal of quantizing, it's also essential to go to the Lagrangian. Why? You can the first thing is the canonical quantization, which means it's the following here. I'm not going to quantize them. I'm just giving reasons why I want to discuss Lagrangian formulation. So in the quantum mechanics, you somehow want to end up with P is equal to minus RH bar X as an operator, and this satisfies. So this is an operator. Let's put a hat. P hat with X hat, or the other way around. In X hat, it's just X, and then you have this thing, and this is what is it? IH bar, and that is the quantum version of the Poisson bracket. Which is 1. And so this is classical physics, and you go to quantum world by copying the equations but giving them new interpretations. That's not the same as that. It's just something else, but it satisfies an equation that we copy from here. You don't have to invent anything, just blah blah blah. But then you need to know what the P is, and the P is defined as the Lagrangian with respect to the velocity. So guess what? How would you get to P if you don't have an L? So we need an L. That's why we're going to do it. That's number one. If you don't like the canonical quantization, but you want the path integral quantization, that's this story. You go from somewhere to somewhere else, and the classical path is this, say it's a free particle and it wants to go from there to there, but the quantum particle can do everything. Right? This is a possibility, at least mathematically. I don't know what the real particle does. You can put a double slit. So here open, they're closed, and they're open, and then it arrives there in funny ways, but you have the feeling it goes to both, like mathematically describe it by something that goes to both. So let's just stick with the mathematics, and so you have all the possible paths, and you have to weigh them with the probability. Like that's very unlikely. This is more likely. And so you weigh them with this action, and the action is the integral of the Lagrangian. So guess how would you do it if you don't have a Lagrangian? Yeah. So we need to go there. Number 5. Lagrangian formulation, I guess. Lagrangian and Hamiltonian field theory. Can I go fast? And with a reminder, point particle. Mechanics. So you have cubes instead of 5s, and you can have many of them. They're functional of t, and alpha goes from 1 to f, and f is the number of degrees of freedom. Right? And then what? I guess you come up with a Lagrangian. I'm not going to go into that then. It is the kinetic energy minus the potential energy expressed in terms of these coordinates. But however you get there, you have a Q and you have a Q dot. And if there's something like an engine that winds up an elevator, or and it could also depend on Q because your potential depends on, you know, that's a general thing. And then the equations that describe the time evolution of these coordinates, like the equations of motion, follow from this. It's the for Euler-Lagrange. Let's first call it Lagrange equations, Lagrange equations. They say the time derivative of dl by dq alpha dot. So pick a certain velocity, take the derivative minus vl dq alpha. You know this thing. That is the equation of motion, or Lagrange. And then you Euler, I guess, stares on this and sees, oh, wait a minute, I know this from somewhere else. This looks like the solution that determines a stationary point in some functional. So now you have a functional S where you can stick in a whole function, U. What's that? What's the difference between a function and a functional? If I have a function, then I stick in an x. So now we're going really back to basics, right? I stick in an x and I get up something. This is the function. Put a value in there. I can even do something funny. I can also put a function inside the function, which means I first go into this first and get a number and then put this and pass it on. That doesn't make anything of this like a function like this. This f just takes the value of the g that g takes for x. doesn't make f a function, no. But if I make it a square bracket, and then let's call it not f, let's call it capital F, so it's a different one. Then suddenly it's a function, no. What does that mean? It means it doesn't want to know only what the g is at a certain position, so not the number, but you give it the whole function to eat. So this could be the f of x. So this is probably let's say a half example, g squared, right? Just stick that value. So the f of x is a half x squared. I don't know why I picked this, but I did. This thing could be integrate all the values. And since that's bored, we square them first. If we're minus 1 to 1, just to keep it bound or something. So then the f wants to know the entire function because it's integrated over it. That is a function. So in this thing, I stick in the whole function of Q. And since I stick in the whole function, I don't really write the argument. It's a Q of T, but what would that mean? So I don't know, I leave it out. And if this is now simply the integral of this L, which has this thing in there, T, then you suddenly need the whole function. You have to put it in. This L is a function of the Q. Just put it in. But this wants the whole thing. And now that's a definition. This statement up there is equivalent to the variation of S equals 0 for variations delta Q with, so this goes from T1 to T2, say, with T1, T2 equals 0. So this you could derive from Newton's equation. You have this in this unrecognizable form. This is the force, the gradient of the potential. This is the momentum. So momentum, this is the momentum. The change of the momentum is equal to force. So that's your Newton's equation. But you can also realize, oh, it's much more fancy. It's like this condition that this function is stationary. If you put in a certain path, a certain function, you get a value. Another path, another value, and so on. And you'll look for that path where this is minimum or maximum, like extremal, so it doesn't change to first order the variation if you hit it. Right? So the solution, classical motion is given where this thing is stationary, the minimum maximum. And all this boundary business just comes with it. If it's not really what I want, but the equivalence is between this and this. So we can just say mechanics works like that. You have this functional and you have these instructions, and that gives you the equations. I can't justify it in any other way. Why? So, example, I guess. Now, what time? Okay. Now let's go to field theory, I guess. I have an example here. So, I feel really dumb. To give you an example, let's say relativistic or let's say a particle with a potential. And then my L is, what is it? Kinetic energy, a half. It's like sum. This is where I want to go. I want you to see the sum. Sum, 1/2 m x I dot squared minus d x1 x2 x2. So this is kinetic minus potential energy, and then something. It's my degrees of freedom are has 3 degrees of freedom. So basically, the alpha q alpha in this case is x I. My variables are now x, and they're by I is 1, 2, 3. And now let's go to field theory. What do I do with this? I have a degree of, I count the degrees of freedom, and then they can change in time. And if I have a field I, well, the field was a function of space-time, and I can write it like this, time and space, so pre-Einstein, like, and then the t is obviously the t, the q is the phi, and the x is the, this is the whole point, the x labels the degrees of freedom. But as an argument, because it's in a continuous fashion rather than a list. But that's it. Now we copy everything here, except for that we turn sums into integrals. So for example, my L, since it's summing over all the degrees of freedom here, I will have to do this there too. So I have d3x. And then, I don't know, something where it disappears, and then probably a time derivative. So why not that? Or even squared, right there. And maybe a half. This could be a Lagrange. And so, yeah, this sum is just that everybody may appear. Every degree of freedom may appear, and then we sum over it, and then we do something. It could appear in a complicated way. I want some restrictions. On L that I give myself. For example, I want locality. That's how we start. What does that mean? If I write a term in this L, which looks like this. Like write 1 degree of freedom at x and 1 of y, and x is different from y, then this violates my locality, because if I derive my equations of motion here, which we haven't written down how this looks like, this maybe we'll do this for tomorrow, then this equation will have fields at x and fields at y. So this says no terms like this. Don't. Oh, cool. But that means it's always the same, like this. All phi's at the same location in the product. All phi's in the product at the same location. And this means my L is, if they're all at the same position, the whole thing looks like something. Well, X. Let's say this. Yeah, let's say this. So it depends. This integrand is a function of my degree of freedom at an x. So you just look what this thing does at the point, and then sum it for all of them. It's not super exact because you also want to, like really the closest neighbors, you want to see how does the field change. So I allow myself to compare positions. So this is also allowed. It is a derivative, but it's sort of derivative at this point. I'm not going to go crazy with more and more and more and more derivatives. Like if I had infinitely many derivatives, I can sneak this back in because with an infinite number of derivatives, I can actually shift my position. Like Taylor expansion is that a function at y, you write it as the function at a different x plus a ton of derivatives of this thing. And if you have infinitely many, then this sneaks back in. I don't want it. So I'm not going to go nuts here with all the derivatives, but I allow them. And here I have the time derivative. So I probably want a time derivative. So I'm also allowing this thing. And then, well, I also want, we're never going to do this in real life, but in principle, I have my x and my t as a variable here that corresponds to the t in there. Now, that's probably a different point. Relativity. Damn it. So here, there would be more derivatives. This is the article is super amazing. There's a line. There's a line. And here, I'm applying all the restrictions. So I have a list of restrictions. And the first one is don't put them at different positions. That means I have this local function of these fields, and I have a lot here. And now I'm restricting this by further constraints. And so there is, like what I know about initial conditions, say that. For time evolution. You know, when you start something, you can choose where you started from and how fast you would set it off. But you cannot choose how fast it accelerates in the beginning in a given system. Of course, you can choose it by turning the force up, but that's changing the system. If you have your pendulum here on Earth, and you can push it or not, you can leave it from here or here, but you can't control the acceleration. That's just how strong Earth pulls. Just by giving it a kick, it's not accelerate faster or anything. So you have to change the mass of the Earth or your pendulum. Well, not even that. And not even that, because it's dumb inertia, right? So it pulls stronger. The force is different, but the illustration is the same. So forget my pendulum, pick something else, like have a capacitor and then the electric field, you can control this. Anyway, you know that. I can choose position and velocity. If I now stick in more and more and more and more time derivatives here, then my equations of motion will have several time derivatives, and then I have to solve them, I have to supply lots of initial conditions, and that's not what I know from everyday life. So that's why I stop here. Just one derivative and not two. The second derivative comes in from here. So this one will already be two. Then comes relativity, and that says time is also just space with a minus sign in the metric. But if you want, then you have to combine it in a way. So if you have only one time derivative, you can't have two space derivatives because it's never going to match. So then these dots disappear. So, I should have probably written the 3 steps to implement all these restrictions, but anyway, after all this, that's the form. This is how it looks like. The Lagrangian in field theory is a local guy, and it's a function. It's called the Lagrange density. Because you integrate over this is in the volume, and then the density becomes the Lagrangian. And if you want to go to the action, that's really cute now. The S is the integral. Nothing has changed there. It's L dt from T1 to T2. And since the L has this form, you have an integral dt dx L. And let's write it now. Let's, I should probably copy this. And then write it v for x L psi of x du psi of x x. Beautiful. So now it looks really like Einstein would have loved it. Partial with a mu for space-time integral. Ooh. In fact, now when we do the principle of least action, that's what it's called, stationary action, then we get equations of motion that will derive, I guess not today, what's the time? No, 1 minute. The equivalence of this for the fields will derive tomorrow. And if this now here is the whole thing is a Lorentz scalar. In fact, since for Lorentz transformations, the Jacobian is 1, because all Lorentz transformations, the proper ones, have determinant 1. So this is the Lorentz scalar. So if you write the Lorentz scalar L here, then we get good equation of motion. This is how we design the theories. And you want gauge symmetry, then you write something here that is gauge symmetric, and then you get good equations. You want charge conservation. Sure, this is all we're going to do tomorrow. Equation of motion and what symmetries tell us here. Point to stop. Yes. Questions?